Ricky, do you want to
Now
start the
recording.
recording? We weren't very formal about starting our hi Don. We weren't very formal about starting our meeting. So yeah, we didn't ever have a point where Ricky could jump in and record now.
That reminds me, you said of a teacher that would give one answer to a test in class. He would just give the answer. So you made sure you would get that one correct if you showed up to class instead of watching it online. So now when you give the test over this session, at least 4 people will be able to get that one correct, hopefully.
Absolutely.
Well, Ricky did start it. Do we want to say that again? Do you want me to stop sharing or leave this going?
No, I think you should leave going. Go ahead. Sorry, who's talking?
I was just going to say really quickly, the answer to Lynn's question was why does the orientation of the interplanetary magnetic field matter to whether or not we see aurora, or the strength of the aurora is to do with the interaction of the polarity of the magnetic field. So if you have 2 north poles aligned with each other, then the only real effect you're going to have is a pushing factor. Whereas if you have the North Pole aligned with the South Pole, then you're going to have magnetic reconnection happening between the interplanetary magnetic field and the Earth's magnetic field, and you're going to have much stronger and much more many more interactions between the two. And so the stronger the interactions, then the more particle acceleration you see in the Earth's magnetic field, and therefore the larger the aurora. So you missed the exciting part of the discussion, but they're the cliff notes that we got instead.
Well summarized.
Thank you, Claire. Thank you.
And you should have come to class.
That's right. For those, we know that you are out there watching this video. We know that for sure because we know, Pandora. We know, Ricky knows how much I love Pandora, so I feel like I'm getting such a treat. And my cat. Anyways, for those of you who are watching the video, and we know that you do because we see the hits, so we know that you are attending, know that you are very, very missed, and that our meetings have not had quite the number of faces that we're used to having. So we hope that you are all well and that you will return to us soon. So, but yes, very fascinating stuff. Anyhow, like I said, how awesome is it that we have not 1, but 2 solar scientists all to ourselves on this St. Patrick Day. So Claire, I won't ask you to model, but just, do you have your kilts on? Woo, look at her, lady.
I only have part of it on because the rest of it is kind of a nuisance. I'll delay the rest of my uniform, but just this is the main piece that I'm missing, my spar, and that won't go on until I actually get to the bar, because there's nothing as embarrassing as walking down the street with a sparring on. At least if it's a skirt and a blouse, people are like, that's an ugly skirt and you have knee-high socks on. But when you put the sparring on, they're like, what is this? So
it all goes to Chicago at all times. So.
I'll have to leave a little bit early today because I have to get down to our gig, but I'll stick around as long as I can.
Well, we're so glad that you were able to make it for a little bit. One of these days, you're going to have to play your bagpipes for us.
I have them here. I don't think it's a good idea. My neighbors probably won't be too happy about that. Nor Brian. Nor Brian.
Oh, well, Brian, just tell him, ask him for forgiveness. Beg for me. Anyhow. Well, we are very, very glad to have Phil Chamberlain with us from Goddard Space Flight Center. He works with the EVE instrument on SDO, and we as many of you know, the community here loves HelioViewer and have had many questions about the different instruments and different data that we are getting from the different instruments. And so I am going to let Phil, I should be reading his bio and I didn't, but Phil, why don't you introduce yourself and tell us all about the great things that you have done, which I'm sure are many.
Ooh. Well, thank you. I'm glad I ran into Claire back in Portland, as I was saying earlier. So thank you for inviting me to give this talk. And I know everybody loves HelioViewer and loves the beautiful images and movies from SDO, the Solar Dynamics Observatory. But just to get a little bit more of my bio, I am the Deputy Project Scientist for the Solar Dynamics Observatory. So working with Dean Pesnell, who's the project scientist. Which is really good, which has really given me a lot of flavor in the imagers and HelioViewer and the data processing of that. But my strength has always been in solar spectral irradiance, especially in the extreme ultraviolet wavelengths. And so hopefully I can convince you through my presentation that stuff is just as important to get the spectra along with the images. And the Solar Dynamics Observatory is really great in that it combines these images with the spectra and with the other instrument, the helioseismic and magnetic imager, to get the magnetic field of the surface and the helioseismology to really give us a complete picture of the sun. And not only a picture of the sun, but how it influences the Earth and other planets, which is where the spectra really come in handy. But along with SDO, I'm also a co-I on MAVEN. That is actually a planetary mission that's going around Mars right now, that I'm sure SSL is very involved with as well. But we have an EUV spectrometer on that. It's a very simple version that I'm not going to get into today. So it's sort of like the dummies version of the EVE instrument on SDO, but still doing wonderful stuff. You have to make some compromises when you go to another planet, unfortunately. And other things, I've worked on sounding rockets. I like to build instruments, do hardware, and I think that's it. I have a very informal presentation style, so definitely jump in here and ask me questions anytime you want, especially with the small group. That's one of the advantages of the small group that I really like, is a lot more interaction. So any questions to begin with? All right.
I think everybody's sitting on their chair waiting to see you.
Well, hopefully I live up to the expectations. All right, so now see if I could remember my tutorial that Andy gave me earlier. Let's see.
It's a share screen at the bottom of the page.
Yeah.
You got it.
Now, are you seeing?
We see your first slide.
The whole thing?
Mm-hmm.
Does it have the toolbar on top of it?
Yes, it does.
Fine.
But that's okay.
Is it okay? Okay. Well, as long as I can, well, maybe it's not okay because now I can't switch. So maybe let me just go to the slideshow and see if it's still okay. Is that good? Better?
Mm-hmm.
Okay. So as I said, I'm going to talk to you today about how we measure the solar spectrum in the extreme ultraviolet wavelengths. And there's my email address. And Andy mentioned there may be some social media thing that I'm not familiar with, but I'm excited to get into and be able to answer questions and follow-up questions once you get more time to digest this presentation. But I've also included my email address, which you're feel free to use later as well. So I'm going to convince you why it's important scientifically, as well as show you some of the details of the instruments that we use in order to measure the solar spectral irradiance. And I just mentioned the keyword, irradiance. This is a spectrum of the sun. And we look at the spectral irradiance, which means we don't care about any spatial information. We look at the sun as a star. So basically, we want to look at all of the light and all the energy coming from the sun to use it as an input, an energy input into other systems, such as the Earth's atmosphere or the Martian atmosphere or the moon as well. So we basically sum up all the pixels, all the light, and we look at the irradiance. And so you can see a spectrum of almost the entire sun. I cut off the infrared as the black body would continue down. But you see, looking at this spectrum of the sun, that we've sort of divided it up into different names. I mentioned the infrared, the very long wavelength portions of the spectrum that are there in the orange and red. The visible that everybody's familiar with, that's your Roy G. Biv spectrum. And it's the dominant portion of the solar spectrum, the highest, the most intense portion of the solar spectrum. And that's the light that all that light makes it down here to the surface of the Earth. Then we get into the ultraviolet light, the greens and the light blues as shown in this figure. And then further on, you keep going, and then you get into, once again, my favorite spectral region, the extreme ultraviolet wavelengths, and then the soft X-ray ultraviolet radiance. And I do want to point out that this is a log scale. There's logarithmic axes on the X and the Y, so therefore each of the major tick marks that you see on the Y-axis are a factor of 10. from each other. And hopefully the X is a little bit more explanatory on how that works as well. But so this is the spectrum, and I still like to throw these in here to get you excited about the sun, and you all love helioviewer as we found out. But this is sort of a movie from HMI, the Helioseismic and Magnetic Imager on the Solar Dynamics Observatory, and this is sort of what the sun looks like in visible light. Not much to it. It's rotating. You can see the sun's rotation, but there's not much activity going on here. You see the sunspots come along. They're not changing that much. No offense, but it's kind of a little boring. There's not many dynamics. And when these sunspots do come onto the sun, the total solar radiance, or the total integrated brightness of the sun, only by less than about 1%. So great stuff there, great science there. But as I said, I want to look at the sun in the extreme ultraviolet. And you could tell from this solar spectrum that the light from the extreme ultraviolet is factors of 10,000 to 1 million times less intense than the peak of the solar spectrum, the visible that we just looked at. But then you can look at your images that you can make through HelioViewer, and you can see that the sun is a lot more dynamic. There's a lot more going on. You see some flares going off there, those very intense brightenings, localized brightenings. You just saw one go off there. You see big coronal holes that are in there. You see big filament channels. You see a lot of different features on the sun that are really exciting. It's really dynamic. And it's not just because I sped up the time lapse and made it go a lot faster. This is about 3 months worth of data from the Atmospheric and Imaging Assembly, the AIA telescope on the Solar Dynamics Observatory. So, and the emissions in this spectral range and in this movie come from about 10,000 Kelvin to, when a flare occurs, they could even be on the orders of 50 or more million Kelvin. So very, very, very hot emissions that we like to look at, and very dynamic.
Can I ask a question?
Of course.
You mentioned the coronal holes.
Yes.
It seems that we have better aurora when there's a coronal hole. What is happening that we get more solar wind from a coronal hole as opposed to a CME?
So what happens there is it's faster solar wind coming out, but it's also an open magnetic field. So the reason it looks dim in these images is that the magnetic field of the sun is open. It's open. It connects from the surface of the sun and goes out into the heliosphere and connects with the heliospheric magnetic field. So there's pretty much a constant stream of particles coming from the sun outward. That's opposed to the closed magnetic field loops that you often see in the active regions, where there's particles that are trapped on the sun. So they don't escape the sun, and therefore they don't interact with the Earth. But when there's an open magnetic field region, like in these coronal holes that is pointed towards Earth, you could get some very fast streaming of particles coming out and increasing the intensity of this reconnection and increasing the energy into the Earth's magnetic field that will cause larger auroras. It's basically a direct connection, a direct link along the magnetic field line connecting the surface of the sun to the Earth. Did that help?
Yes.
Hopefully. Okay, great. And so these coronal holes are very prevalent, and you can see them very well in the EUV sun.
I have a separate Bill, this is Andy.
Okay. Yep.
And it's along with that though, and this is really dumb and really elementary. So does that affect so in my head, if there's more solar particle streaming more quickly, right, because of the coronal hole, does that mean that the aurora effect will be larger and can be seen further south?
I think they are more intense. This is a little bit beyond where I'm coming from the magnetic field interaction with the Earth's magnetic field. But the largest, I will answer by saying the largest ones that you could see further down south come with coronal mass ejections, where, as we were talking earlier, where you get a whole blob of plasma that comes off with the magnetic field opposite of the CME to the Earth's magnetic field. So you start getting magnetic reconnection. That's where you get the very largest of the auroras and that go down much further into the lower latitudes.
Gotcha.
The solar wind is going to increase the intensity of the auroras, but still they're going to be really far north, and they're not going to be as intense as the ones you get with coronal mass ejections.
Okay, thanks.
So this is my sort of generic cartoony-ish almost plot of the solar irradiance spectrum, but now I'm going to focus on the extreme ultraviolet. As I said, this is going to be a talk on these very high energy, very short wavelength solar photons. So we're going to zoom in on that spectrum a little bit and start looking at an actual spectrum. And once again, this also helps point out some of the definitions that I talk about. You see the black body irradiance coming in from the right-hand point of that plot and dipping down lower. And the black body, as I said, is formed in the photosphere. So formed in the surface of the sun from the approximate temperature, the 5,700 Kelvin photosphere. But then as that black body falls off, as you go to shorter wavelengths, you start to get this very grassy, this forest of emission lines that are formed in the solar atmosphere. So these are mostly ions that are formed at really high temperatures, as I mentioned before. And you can see a lot of emissions from different portions of the solar atmosphere. And by emission lines, I mean by when you have an atom, such as carbon or hydrogen, and you get the electron kicked up to one of their higher quantized levels by any of the various processes from collision or photon absorption. However you get that electron kicked up to the next highest energy level, it will then decay back down and emit a photon of that discrete energy based on the atomic separation. And therefore, they give very discrete lines. And so you can look at this solar spectrum and you can see carbon, you can see silicon lines, you can see helium, you can see iron, you can see neon, you can see magnesium, and you see them in various ionization states. And basically what you have is the higher the ionization state, or the more electrons that are kicked off, is proportional to the temperature of plasma at which they're formed. Higher temperature means you're going to have more energy, you're going to have a higher ionization state, or more electrons kicked off, and therefore you get different emission lines from that. And so you can see all sorts of them, and they're color coded here. The blue lines are formed in the chromosphere, so the layer just above the solar photosphere. And there's a plot on the right, and solar physicists a lot of times like to put height on the x-axis and temperature on the y-axis. So I switched it in the next version, so maybe I'll do half of this with this orientation, and I'll flip it around, but it changes all the words. But so you can see that the photosphere is sub 10,000. It's anywhere from 4 to 5,000 to 6,000 Kelvin temperature, where the black body is. Then you get to the chromosphere, the next highest layer, which are those blue lines, the silicon one, the carbon one, emission lines that you see in the left plot. And they're on the order of tens of thousands of Kelvin. And then we move up higher. You have the coronal heating problem. Which is one of the big questions in solar physics. How does the upper portion of the solar atmosphere become so much hotter than the lower layers of the solar atmosphere? That's not how physics is supposed to work. The simplified physics is supposed to work anyway. And so we get into the transition region, where this transition and great heating occurs from the tens of thousand Kelvin up to the 1 million plus Kelvin very rapidly. And you see all these emission lines that are in red on the left plot that are formed in that region that are corresponding to temperatures of hundreds of thousands of Kelvin. So we're starting to get warm. The helium 1, the oxygen 4, the carbon 3s. You see all those lines there. Then you get to our really hot lines that are formed in the very hot corona. That's on the order of 1 to 2 million Kelvin. You get these iron and these magnesium 9s, magnesium 10s, these really highly ionized ions that give their characteristic emission lines there. So when you look at the EUV spectrum, you're really looking at the solar atmosphere. You're looking at different layers of the solar atmosphere, and you're looking at different temperatures as well by being able to look at all of these simultaneously. And as I mentioned, this is just a solar irradiance spectrum of sort of a quiet time. But if you look at solar flare emissions, you could see some of these extremely ionized, some iron 24s, iron 25s that can only be formed that have characteristic temperatures in the tens of millions of Kelvin, sometimes up to 50 megakelvin, which are very, very hot plasma emissions. So this is all the gory details of the EUV spectrum. And as I said, I wanted to switch it so that height is on the left axis. It just seems more logical to me. And then temperature is increasing to the right on the x-axis. Sorry, height on the y-axis. And you see sort of the temperature profile is just a solid line. You see the huge increase, the huge jump in temperature at the transition region height. And I know you can't read the words, but hopefully you got that. And obviously we've all heard the term the solar constant. The sun is not constant. I'm sure you guys all know that now, 100 years later, but there are still people out there, and maybe some politicians too, that believe that the sun is constant and it doesn't drive any changes in the Earth. But we all know that's incorrect, and we have measurements. You can see in the top left plot, there's variations in the solar irradiance at all wavelengths, not just UV, at all wavelengths, on the order of months to years, having to do with the solar cycle, the 11-ish year solar cycle, where you get an increase in the number of sunspots, the increase in the number of active regions, the increase in the number of flares and CMEs at different times that go on sort of a waxing and waning 11-year period. But you can also zoom in a little bit more, and you get activity on the order of days to months. This has to do with the sunspots and the active regions coming around sort of like a lighthouse, a beacon sweeping across the surface of the sun as we see it, as the sun rotates, and causing an increase in energy input into the Earth and then a decrease. And so you see a sort of 27-day solar rotation period as well. And then we have the solar flares, which you saw a lot in that beautiful AIA movie, which is often probably the most searched thing with HelioViewer, is people making movies of solar flares. And these could have huge increases, factors of 2 increases, factors of 100 increases in the X-rays on as quick as, in a few to tens of seconds. You could get the increase in these wavelengths. So we really have to look at timescales of seconds to hours to months to years to decades, even to billions of years now, if you start to look at climatological scales. Unfortunately, we don't have SDO pass, we've had SDO for 5 years now. We haven't had it for 4 billion years, which would be nice, but apparently technology's come a long way since 4 billion years ago. So we want to measure the solar radiance on all of these timescales as well as we can. And why? Why does it matter? I mean, if the EUV, extreme ultraviolet irradiance, the intensity is 6 orders of magnitude dimmer than the visible light, why does it even matter? And this graph very clearly shows that the energy from these wavelengths are absorbed and deposited up in the Earth's upper atmosphere, which is very fortunate because these really high energy photons would, if they reached the ground, would give us really good sunburns and a lot of other harmful things that come along with EUV and X-ray exposure. But what this plot shows as a function of wavelength, so a spectral distribution of where the energy from the sun is deposited in the Earth's atmosphere. The really bright, hot colors are where you get the most energy deposited, down to the cooler blues and the blacks, and the white is where there's no energy deposited. So you see 100%, all of the energy is deposited from the extreme ultraviolet wavelengths up in the upper atmosphere, from about 80 kilometers up to well above 500 kilometers. This is what creates the thermosphere, the heating of the Earth's upper atmosphere, as well as ionizes the atmosphere, kicks electrons off to create the Earth's ionosphere. And this plot right here is at solar minimum. This is taking a solar minimum EUV spectrum, folding it through all of the things that make up the Earth's atmosphere, all the nitrogen, the ozone, the oxygens, folding it through everything and determining that. But if we take a solar maximum spectrum spectrum during the peak of the 11-year solar cycle and push it through the Earth's atmosphere. This is what the energy deposit looks like. So I can sort of flip back and forth, and you see how much different the scale, the color bar scale is the same. So you can see how much more energy is deposited in the Earth's atmosphere just between solar minimum and solar maximum. You can also see other things. If you're familiar with the spectrum, the helium-2 304 line. So spectrally, you can look at the 30.4 line on the x-axis, and you can see how bright the emissions are just due to that line. Well, that's a very strong line in the solar spectrum. And so you could kind of see a solar spectrum superimposed on here, where you get more light from these strong emission lines from the sun. You get more energy deposition at those altitudes. So just to flip back and forth, you can see the difference again. And so what does this do? You get more energy deposition in the Earth's atmosphere. Great. What does that mean? That means you get changes in, as I mentioned, you get changes in the temperature. The neutral temperature could change by a factor of 2 between solar minimum and solar maximum. The electron density, as I said, the more energy you put in, the more electrons you kick off, and the more ionization occurs, separating the electrons and the ions, and you get an increase in density by 2 orders of magnitude in the neutrals, and 1.5 orders of magnitude in the electrons. So you get huge changes in the constituents in the ionization of the upper atmosphere, and it's a function of height as well. You get stronger changes at different layers where you get more energy deposition, as I showed on the previous plot. And then these physical changes, obviously these are changes in density and temperature of both ions and electrons. I did insert this. So this is just a simulation that we've done that shows globally, shows images of where the changes actually occur. And they obviously occur at this sort of subsolar point, are influenced more the location where the sun is directly over when a flare occurs. So this shows, in this one, shows the electron density at, I believe, about 100 kilometers altitude over the globe when a solar flare occurs. You can see that the third Earth model in shows a huge increase in the electron density on the Earth when a flare occurs, and then you see it subsides over the next few minutes to hours. And the time scales of this influence are very equivalent to the time scales of the solar flare itself, which the strong solar flares can last anywhere from tens of minutes to hours. Some of the largest solar flares can occur, 8 hours to 12 hours, and you get equivalent time scale increases in the density of the Earth. So those will then all drive. I think you've all heard what the quips about space weather and the one-liners. All of these physical changes influence global positioning system. The accuracy of the global positioning system influences shipping and navigation, influences magnetometers, drives currents that can influence the degradation of oil pipelines going from Alaska down to the States. Those could degrade faster with the induced currents. Radio communication, if you're trying to bounce radio waves off of the ionosphere, if the ionospheric density is changing and the different layers are changing, they can be influenced as well. And I think I have some more influences in here later as well. But what I wanted to make sure I had time for is to get into some of the hardware. Is there any questions on the science? I want to take a little break and make sure sort of the science was covered and fairly clear of why we want to measure this.
I know you've given me some really good things to consider, Phil. I felt like it was really comprehensive, that I saw a bigger overview. As much as I've heard some of this information before in various places, it all kind of put it together for me. So thank you.
Great, thanks. So, and one of the reasons I got into this field, I guess I should have given you this in my bio, but I was a physics major as an undergraduate in Hanover College in Indiana, but then I switched to aerospace engineering sciences for my PhD at the University of Colorado, because as I was going through the undergraduate physics curriculum, I realized I was really an experimentalist, that it's really cool. I love doing the science. I love doing the computer programming and the data analysis. I love spending some of my time sitting at a computer doing science or a notebook doing science. But I also need the part, the other half of me where I'm actually working on hardware. I'm designing instruments. I'm in a lab. I'm taking measurements. I'm doing things with that are hands-on as well. So I switched to aerospace engineering sciences, and I found a very good mix, very good relationship between the science that I love, pushing the boundaries, discovering new things, as well as designing instruments, building instruments, launching rockets, launching satellites, which is really cool. So I also am now going to go through some of the hardware aspects of measuring the EUV solar radiance. And this is just a picture I pulled off the web. I'm just doing a quick search. This is about as simple as you get in terms of a grating spectrograph. So what you have is just an entrance slit which you point at the sun. The light comes through that entrance slit in the top there, goes off of a grating. So this grating diffracts light, separates the light from all wavelengths, from the white light or the entire solar irradiance into its different colors. And the grating will cause the colors to come together to diffract some focus. It's like a telescope, as well as separating the light. It also focuses the light with one element, so that you get all your, in this case, reds coming together at one point, greens coming together at the other, and blues coming together. So this is a very simple concept of an EUV grating spectrograph. Some certain aspects about doing optics in the extreme ultraviolet, if you're not familiar with it, it's very contamination sensitive, as in any oils and greases from your hands, any other thin films, like you can't use Windex to clean your optics. That will leave enough of a little film that will completely wipe out any reflectivity that your optics have. Oils are the really bad things. So you always have to make sure you're in a clean environment. You're in a clean room doing these. You have gloves on, the bunny suits, to make sure you keep your instruments clean. Also, they have to be all reflective optics. If you try to use a lens or a refractive optics where you try to focus light with a lens, there isn't glass that transmits below about 119 nanometers. That's about the low wavelength cutoff to use glass focusing refractive systems. So you have to use an all reflective system. So we're stuck using mirrors in order to do our focusing and reflective gratings as well. We can't use a glass prism to disperse our light into its wavelengths. So it makes things a little more difficult, but there's tried and true methods on how to keep things clean and very good optics and that we can use. So we found ways around it. But this simple concept, as you're looking at right here, was pretty much the concept of the first instrument that I worked on as a graduate student. It is the EUV grating spectrograph, which is one component of the solar EUV experiment, the C experiment, on board the timed satellite, where time stands for the thermosphere, ionosphere, mesosphere, energetics, and dynamics. So a lot of acronyms, which I'm sure you're all aware of, working with NASA and in the EPO world. We all love our acronyms. But just looking once again at the basic concept of an EUV grating spectrograph, which is exactly the name that we call this instrument, you see the slit, basically the entrance aperture, which is that black thing in the lower left. My pointer unfortunately doesn't work in this presentation mode, but you see the little black square in the lower left of that instrument is where the slit is, and it has a piece of tape covering the slit so that we don't get dust in it, because it's a very fine slit. The thinner you have the slit, the better spectral resolution you can get. So the light will enter in that little slit, and it will go to the back, so the top right of that instrument. And the top right of the instrument is where the grating is, the holographic focusing curved grating that will disperse the light as well as focus it onto the detector, which you see it's a Kodacon detector as it's labeled there. The 64 element by 1024 element Kodacon detector is where the camera system is that will take a picture, and you can see an actual spectrum that we have taken using this instrument there that's false colored in sort of a red temperature heat map. And then, which is the middle, and I've labeled some of the lines that you can see. As well as below it, if you collapse everything down, so if you smush the slit, you can see all the slits that are vertical, that basically you use the longer slits just to get you more signal. And then you disperse the light to get your spectral information. But when you collapse down, you basically sum that image down and integrate, you get the spectrum that you see lined up below it. That has the wavelength scale there, and you can see a lot of the strong lines coming out that are labeled. And this one actually goes out to 190 nanometers, so it includes some of the black body continuum that you see coming down there from the right, as well as a lot of those strong emission line features that we had talked about that are very prevalent and dominate the EUV spectrum. So this is and by the way, I have to tell the story. I first was introduced to this instrument my first day in the lab. I show up as a graduate student, 22 years old, meet Tom Woods, who is my advisor. If you know him, great guy, amazing guy, brilliant guy. So I'm coming up, a nervous graduate student, seeing my first little bit of space hardware, which was this thing. And it has an ion vacuum on it. So you basically want to keep these things clean, so you keep them in vacuum. So it's got its own built-in vacuum on it, and the vacuum wouldn't spark. It wouldn't start up. You have to get an arc going that causes a vacuum, but it wouldn't spark. So what he does is he comes and takes a wrench, and he goes and he smacks the vacuum a little bit with the wrench. And this is a spaceflight instrument that was going on a sounding rocket. Apparently, he just needed to knock the dust off of it so he would get the spark to fire on this little built-in pump. So that was my introduction to spaceflight hardware. Is if it doesn't work, hit it with a wrench, and it fired right up. So I've learned better principles since then, but sometimes you have to go with what you learned. But this launched, the Time satellite launched with this on it in 2001, started taking measurements in 2002, and it's still working today. So we have a very long record of very good solar irradiance spectra since then. Then, if there's no questions, I'll move on. Then Tom Woods and his group was selected while I was finishing up my dissertation to build the Extreme Ultraviolet Variability Experiment, or the EVE experiment on SDO, the Solar Dynamics Observatory. This is basically the follow-on, the grander, the bigger, the better version of the Time C instrument. Time C was great. SDO EVE is going to be better. Better wavelength resolution, better time coverage, temporal coverage, better accuracies, and bigger and more expensive as well, which I think those things are, you want a better instrument, it's going to cost more. And what you can see, this is its sort of baby picture after it's built, before it's shipped off to go meet the satellite. And you can see there's 4 different channels. You see the 4 different entrance apertures there, 3 of which are rectangular. The 4th one is circular. And I'm going to focus on, because I'm really just focusing on EUV grating spectrographs, I'm going to focus on the middle 2 channels. If you want some follow-up on the left one, which is the ESP channel that was built out at University of California, Southern California, let me know, just south of a lot of you guys. And then we also have a little pinhole imager. That's the far right one, which is probably a simple one as teachers that you may have made. Just take a cardboard box, put a pinhole on one side, you know, a screen on the other side, and you have a pinhole camera. Well, that's pretty much what we made on that right side. It's called SAM, if you've seen it, Solar Aspect Monitor. But that's just a little quick thing on those two end instruments. But I'm going to focus on the middle two instruments, middle two channels for this talk. And here you see it mounted onto the SDO instrument module. So this is in the Goddard clean room with all its protective red tag covers on it. The red tag means we need to take that part off. It's just a protective cover, so make sure you take it off before launch. And you see the doors are all closed up too, protecting the inside of the instrument on those channels, where it's open has the doors open on this picture. These doors are all closed just to keep it a vacuum, keep it clean on the inside. And now I'm just going to take a little cutaway, go to a little cartoon version, and once again in the hardware to show you sort of the optical channels that I'm talking about. These aren't too bad. I'll just start with MEGS A. You see the MEGS A channel labeled in there. This is pretty much the same sort of thing. The light comes in, the sun is on the left. And so in MEGS A, where it says MEGS A, the light comes in, goes through a slit that's right above the A grating. It's right above the A on the label A grating. It goes off the grating. The grating disperses the light as well as focuses the light onto the MEGS A CCD, which is labeled CCDA. Very simple sort of design. I'll get into a little bit more details. MEGS B, once again, this almost the same thing. The light comes in the MEGS B channel from the left, goes through a slit. It goes off a grating, which is the very far right element. The grating disperses the light as well as focuses, and goes to another slit and then goes off another grating, which I'll get to why we have two gratings in this system as opposed to just one. And then it's focused then onto the MEGS B CCD, where we could take the picture, read it out, and then downlink it to a scientist on the ground. And as I mentioned, there's lots of other things in here, but just keeping the talk focused. So this is the MEGS A channel, and a little more, first of all, breaking it out to simplify things, but showing the actual ray trace in a little more detail. We have our entrance slits there on the left, and we actually have two entrance slits. So we have two slits stacked on top of each other, which basically makes two channels out of, while only having to use one grating and one CCD. And the reason we have to do that is we need to isolate different wavelengths of the spectrum. So we have different filters. We have different bandpass filters on the top channel versus the bottom channel, which we put right in front of the entrance slits. And you can see that the top one, the bandpass, the transmission as a function of wavelength of the specific filters that we use for the top channel on the top right plot and the bottom channel on the bottom right plot. And basically what you're doing is you're just depositing thin layers of various elements to block off some wavelengths from entering the channel, but then making sure you're transmitting that the light that you want to view actually gets through that channel. So you see the MEGS A filter will let in wavelengths from about 5 nanometers up to maybe 17 or 18 nanometers, and it will only let that amount of light through, light from those wavelengths. Then the bottom channel, the MEGS A2, has different elements and different layers of different elements in order to let light in from about 16 nanometers, 16 to 17 nanometers, all the way up to 40 or a little bit more than 40 nanometers. So you're basically using these different layers to isolate portions of the spectrum that you want to see. So we get two channels in this MEGS A. We get MEGS A1 that goes from 5 nanometers to 17 nanometers, then MEGS A2 that goes from 17 nanometers to about 37 nanometers. So light goes in, goes off the grating, that is then focused onto the detector face. And so we're basically having to use different optical techniques in order to get the complete spectral coverage that we want to cover the entire EUV wavelength range. So that's MEGS A, and this is what the detector then looks like. This is actual solar data. It's actually from a sounding rocket, but it's basically a clone of the Eve instrument. And so you see those two channels. You see the top slit that goes, the top and bottom slit that go, both of them go off the grating, and then both that are dispersed along the detector. And you see the different wavelength ranges. Wavelength is actually short wavelength on the right, long wavelength on the left. So your right edge is pretty much about 5 nanometers. The first lines that you start seeing on the far right are about 5 nanometers. And then your strong wavelengths on the left are about 37 nanometers. And you see these very bright slit images that are dispersed along the detector. And you see that the top right one has the bandpass that goes from about 5 nanometers to about 17 nanometers, whereas the bottom one has about 17 nanometers to 37 nanometers. So we're isolating those two portions of the spectrum. But I think this is just, this is beautiful to me, to see this and see how well it worked. And you false color it purple just to show the intensities. And then once again, I could zoom in to the MEGS A2 part. So this is the bottom left, pretty much portion of the spectrum that you see here, the bright bottom left. I just cut it out and I labeled some of the emission lines that you can see from the sun. You see these bright iron 9 lines that are around 17 nanometers that are formed. And then you see the extremely bright helium-2 304 that's commonly referred to 30.38 nanometers, which also makes some of the beautiful images. If you, instead of making a spectrum and you just use one of these filters that I talked about and isolate this line in a telescope, you get the AIA 304 images that show the really good prominence eruptions and beautiful features if you're into imaging and HelioViewer. But this is what it looks like spectrally and how it compares to the rest of the lines. And now moving on to the second channel from SDO Eve. This is the MEGS B channel. By the way, MEG stands for multiple EUV grating spectrographs. We basically had to do multiple channels of EUV grating spectrographs because you need to use different techniques for different wavelength regions across the EUV. And you see that this one actually has its entrance slit there in the middle. It goes back, goes off its first grating. That grating disperses the light as well as has some focusing elements because it's a curved grating. And then that goes through a image. You see it's the image of it's labeled first image of the slit. So basically we put another slit on there because we don't have filters that to isolate these wavelength ranges because we just couldn't find layers of elements that we could really isolate this wavelength region. So what we had to do, instead of using filters for this channel, we just have an open entrance slit with no filters in front of it. We bounce it off of a grating which disperses the light, but then we use a second slit to just mechanically, it's like a baffle. We block off all the other wavelengths by putting mechanical structures there while we only have a slit that then lets the portion of the spectrum that we want through to go through. So the portion that we want, it's a mechanical bandpass limiter, then goes through to the second grating, and the second grating is actually rotated. Its grooves are rotated 90 degrees from the first grating. That will then disperse the light again. And the reason for these two gratings is we have to eliminate higher orders. The bandpass that we're trying to get with this spectrum is from 37 nanometers up to 105 nanometers. That's a very long wavelength region to cover. And the problem is second order and third order and fourth order light. So basically, if you have light coming through, say you have a strong line at 40 nanometers, you're going to get a second order line of that strong line at 40 nanometers. That's going to be at 80 nanometers, which is still within our bandpass. And we want to make sure that we don't say, hey, look, I found a new spectral line at 80 nanometers, when it's actually, we're just looking at the 40 nanometer line in second order. And so because we have such a large range, once again, from 37 nanometers up to 105 nanometers, we could get first order light and second order and third order in there when we only want the first order. So this is a way, by using these two gratings, we separate all of these orders so that when we get the spectrum, it's only the first order light. And we know we're seeing a pure first order solar spectrum. So it was a very clever idea from our optical engineer on how to get rid of these higher orders. And because we have two gratings that are rotated 90 degrees, our spectrum actually goes diagonally across our detector. And so this is once again actual solar image, solar spectral image of our MEGS B detector. You see our prime first order light going across the center there. And then you see these higher order lights. You see some in the bottom left, which is higher orders that we want to kick out. We don't want to use those because they're not part of our primary spectrum, our primary spectral range. You see others in the top right that are a little bit dimmer. These higher order emissions are dimmer, are weaker. This is just how the gradient equation works. But we really are only focused on that center swath right through there. So those are our two channels that I really wanted to cover. So I went quickly over times C and then our new instrument, SDO Eve. But when you're designing an instrument as an instrumentation, you want to sit down and you have goals that you want to design goals that you want to get. And I just wanted to cover. First of all, I'll just pause once again. Does anybody have any questions on SDO Eve or time C or anything else, I guess? All right. So I'll keep moving on. There's sort of 5 design goals that you want to get. Obviously, you want to build the best instrument possible for the budget that's allotted, which is key these days because with tight budget constraints. So one thing you want to make sure you cover the entire spectral range. This is why we needed all the different channels on Eve. We needed the 3 different channels, so we made sure that we covered the entire spectral range. So this is a solar spectrum from time C actually because it has a larger range. Time C actually goes from 27 to 190 nanometers, whereas SDO Eve was pushed shorter. We could cover shorter wavelengths starting at 5 nanometers, but it only goes up to 105 nanometers, which is because we wanted to satisfy another different goal, which I'll come to. You see, time C covers the entire spectral range so that we can get all of these energy inputs as a function of wavelength to the Earth's atmosphere. And then, so our goal number 2 is we want the highest spectral resolution possible, which means we want the sampling quality along the spectrum to be much better. And this is why SDO Eve doesn't cover such a large range, because we wanted much more spectral resolution, and we get a factor of 10 better spectral resolution than SDO Eve got. So here I could just switch back and forth between the 2 spectra and see how much better, how much more detail is in the SDO Eve spectrum than the time C spectrum, which really helps us do a lot of solar physics as well as energy inputs and other space weather studies. So the third goal is temporal range or temporal coverage. As we mentioned, the science is all the UV light gets absorbed in the Earth's upper atmosphere, creates the thermosphere and the ionosphere. That also means that we can't use ground-based telescopes to look at the light because none of it gets down to the ground. So you have to go to space to measure this. And as you can see by this graph, time along the x-axis is a function of wavelength along the y-axis. Measurements have been very sparse of the solar irradiance in the EUV and ultraviolet wavelength ranges up until the launch of TIME, which launched, as I said, in 2001, started taking data in 2002. TIME really started filling a gap. And as I mentioned, this graph hasn't been updated for a while. I got this from Tom Woods a while ago and still use it because I like it. But TIME is obviously still going now that we're in 2015. SDO has launched. Wow, 2008 it was supposed to launch. So it actually launched in 2010 and is continuing on in some ways. We've lost some channels. We lost the MEGS A channel, which unfortunately suffered an anomaly that took it down May of last year. So we lost that wavelength coverage from SDO Eve. But as I said, TIME continues on. So these bars are now marching along to the right, which means we really get to cover large temporal range, time C is now at over 12 plus years. So if we want to study the solar cycle, we have good coverage over from the peak of solar cycle 23, the peak of last solar cycle, all the way through its decay, as well as max of this solar cycle as we go towards its decay. So if we want to study solar cycle variations and solar cycle studies, we have a very good database between timed and SDO, as well as source in there that has a solstice instrument, which I didn't talk about. I can if you like, and you have any questions on source solstice that covers the FUV wavelengths. I'm also happy to talk about that offline or through your social media, or give you links to that as well. So you want something that's going to be up there for long duration. We also, goal number 4 is temporal resolution. As I mentioned, flares cause an increase and decrease in EVs on the order of seconds to minutes. And so therefore, if you want to see a flare go up and down within an hour, you need to make sure you have enough temporal coverage to get multiple measurements throughout. And SDOE fortunately has a measurement every 10 seconds and almost 24 hours a day, 7 days a week when both channels were functioning properly. So we're able to see, this is just an example of some time C data during a flare. You see it's about 2 hours worth of data on the x-axis, and you see different wavelengths that are formed at different temperatures. And you see that we get to see all of this change. We get to see the very sharp rise that occurs on the order of 5 minutes for some of these lines. We get to see the multiple pulsations that are in there. It's not just a smooth rise and a smooth decay. There's a lot of structure within there. As well as some wavelengths are offset. Some wavelengths peak before other wavelengths. This has to do with the heating and the cooling of the flare plasma. And if we didn't have a measurement every 10 seconds, we wouldn't be able to pull this information out and study these heating and these energetics of solar flares. And goal number 5 on here as well is accuracy. If we want to see and we want to know that all these little smaller pulsations that you see, especially in, say, the red line, are real, that are real solar variations, then you have to make sure that they are actually statistically significant, that the signal is more than the uncertainty in the measurements, which also gets into precision. So we know that this isn't just noise. This isn't just our electronics not being accurate enough to measure these smaller variations, that we know that these really are solar variations. So you see that time C only took one measurement every 96 minutes. That means we would only get one measurement, maybe 2 in this entire time range. So it's really hard to study flares with time C, whereas SDOE takes one measurement every 10 seconds. And the accuracy, time C, was only accurate to about 10 to 50%. So based on the wavelengths, you would assume that these pulsations that you see in the red line, they could actually just be uncertainty. They could be electronic noise. They could be noise in your detector. You can't say these are definitively solar variations. Whereas SDOE, much better. We have uncertainties in our accuracy of 8 to 15%. So much better, much more accurate, so that we can know they are solar variations. So just to conclude, hopefully I've convinced you a little bit about spectroscopy, and although we don't get as pretty of movies as the Atmospheric and Imaging Assembly, the AIA, we get a lot of really good, valuable data that not only we could do solar physics with, but space weather studies as well, both here at Earth and at Mars and on the Moon, which all have been done. And SDOE was able to measure and satisfy all of these 5 major goals that I just went over. It has the spatial range and resolution. It has the temporal range and resolution, and is a very accurate measurement to do the science that we needed to do. And lastly, I covered EUV grading spectrographs. I covered one portion of the solar EUV spectrum and 2 instruments that have measured this, that have a couple channels, but there's obviously a lot of different ways that these measurements can be made, some better, some worse. There's trade-offs and everything. There's different measurement techniques to study other portions of the solar spectrum. Once you get to soft X-rays, there's completely different technology that's needed. When you go to infrared, completely different technology. So I just chose to focus this talk on what I am used to talking about, and what my specialty is. But there's definitely a lot of other science goals that can be done with this, as well as other measurement techniques. So that is all I had for you, and I would be happy to take any questions or discussions that you would like.
That was so great, Phil. Thank you so much. I love hearing about how the different, I like seeing the insides of the instruments and understanding how the information that we do. So that was really helpful for me. Any questions or comments for Phil?
That was cool. I enjoyed it. What's the next generation? If we've jumped that far from the time C to the SDO, Eve, how soon till the next generation? What kind of things do you want to see on your next one?
That is actually kind of scary, because with budget cuts and the lack of big missions and lack of even small missions such as the Explorers, the SMEXs, going up, there has been no talk of an SDO2. There's nothing to replace AIA, EVE, or HMI even being planned right now, which is very unfortunate, because they're all working on other things, other gaps that need to be filled because we're not getting the frequency of launches. So we're kind of hoping that we could first get more measurements. It's unfortunate that EVE failed because we're missing a lot of data. We only had 5 years of data with some of these channels. And unfortunately, what they're going to rely on is modeling. So use that a lot of it's proxy modeling, a lot of it's physical modeling. So taking relations such as all of these wavelengths to the magnesium 2 quarter-wing ratio, a lot of these measurements that NOAA SWPC makes. And it's going to make, so they make 5 measurements along that spectral range. And you have to use statistical models to then predict what the entire solar spectrum would be based on these simplified 5 or subset of measurements. So there's no actual measurements. There's no next generation EVE being planned. Unfortunately, the community is going to have to rely on models, rely on the data we have to then sort of estimate in the future what the solar irradiance is doing. And that's kind of, unfortunately, that's where it's at right now. Not just for EVE, for AIA. There's no follow-on to AIA. Fortunately, it's very healthy and very good state, as well as HMI, magnetic field stuff. Then you get to coronagraphs. Coronagraphs is even worse. They're relying on SOHO right now. Stereos are having some issues just because they're behind the sun. Hopefully they come back and they're healthy. But when you look at coronagraphs, the other big thing that is sort of missing from SDO, I mean, we're relying on SOHO that's 18, 19 years old now to get that measurement, with nothing planned coming up in the future. So we're going to be hurting in all aspects, not just from solar spectral irradiance.
Wow, that's kind of sad, isn't it?
Yeah, I mean, it is sad. I completely agree. But on the positive note, Solar Pro Plus, the next big thing that is coming up, is going to be amazing. It's going to get new measurements. It's going really close to the sun. It's all in situ stuff, so it's a lot of outflows, a lot of these solar wind questions, magnetic fields. Solar Pro Plus is going to be great. It's different. It's new. It's not just repeating the same measurement better. So I'm really glad that they took that step. NASA took that leap to go for it. It's just going to be expensive, and it's gonna really hurt the budgets to do anything else. But I'm still all for it. I can't wait. I have no part of Solar Pro Plus, but I can't wait to see the data. It's going to be great.
I think a lot of people are excited about Solar Pro Plus. So
yeah,
fingers crossed. Diane, you were talking about how you've worked with timed before, and in the comments you said that you felt like you stumbled through in it being explained, being able to explain timed. Was that you? Oh no, it was Dawn. I'm sorry.
Yeah, that was when I first came on board to APL. That was one of the first things that I talked about when I went to the Heliophysics Educator Ambassador Conference in Alaska.
Yeah, APL. That's where time just run with Sammy and El Sayed was part of it as well before, which he now moved on to headquarters.
Yeah, El Sayed was my teacher. I was sorry to see him go.
Yeah, oh, he's great. He's absolutely wonderful. So yeah, I missed all the comments because I was in presentation mode. So I'm trying to scan them real quick, but
that was the big one. I would have interrupted otherwise. I just left
Okay.
that one for the end for that. So no, excellent. Hopefully that everybody found this helpful. I know it helps, just remembering where the place for spectra is, and how
Yep.
it's something that, that was really helpful because students and the teachers I work with want to know, how is it that we know that from looking at those things? And especially when you talk about different ways of seeing, invisible light, and how, even some of your words from the presentation, like, why we can't study the sun from ground-based telescopes. And, the first answer is because it's too bright, but to remind us that our atmosphere really does leave out a lot of information. Thankfully so. I'm grateful to our atmosphere.
Yes, exactly. We'd be in a lot worse situation if we didn't have it.
But again, what happens when we just step outside of our own back door and just look a little differently? How exciting it is. So,
yep.
Any other questions for Phil, or any discussion pieces that you wanted to bring up? I know that this is really helpful. Yeah, like I said, it's really helpful for me to see the whole picture and see where I think what I love about this community is I'm starting to see where all the pieces fit together as far as solar science, and get a big.
There's a lot of pieces, as well as a lot of pieces that overlap with planetary or overlap with Earth science.
Yeah.
I mean, it's heliophysics. I mean, it's very, a little bit here, a little bit there, a little bit spread out, not just within solar, but also within the other communities and relevant to other communities.
Well, and what works for our star works for other stars too, right? And
exactly, astrophysics. So Kepler, Kepler has been amazing. I just had a talk with a guy today for about a half hour before I had to run another meeting about looking at Kepler stars. Or Kepler
good.
Kepler. So they saw a flare on a sun-like star, sun-like twin, that was 100 factor of 100 larger than any flare we've seen on our star.
Wow.
So
that's new information.
And he starts getting into the biological aspects. And if you have that, you could actually start having enough energy to create life, the building blocks of life, which I think he started going off on a deep end, but he believes it. He's a very brilliant guy. And so he started like you don't need lightning. You just need an SEP, a CME, and a flare that are much more globally spread than the localized lightning. So
absolutely. Yeah.
So there's a lot of really cool astro as well. And Kepler's seen this on a sun-like star, which is scary in one sense, but pretty cool in another.
Absolutely. Yeah. And to be able to make those connections, because that's definitely where, teachers and for sure students are at, is, they want to know, well, how can if we can't actually see it, how is it that we know so much about it? And spectroscopy is often where I go with that, to say, well, we can take measurements of light and we can look at what is comprised out of that and kind of bring up those pieces. So to be able to do that with our own sun is just fascinating. So thank you so much for all that information. I did send you a invite to the WIGIO, and so that
Great.
if you choose to accept this mission, you can post your slides, and definitely will be a place where others can ask questions or totally can respond to anything that anybody has, or remind us where we need to bring in spectra.
Yes.
To be able to look at the data together. Well,
wonderful. Yeah, I'll definitely do that.
Thank you.
I think my slide, I converted it to PDF and it was 17 megabytes still, so I have to reduce some sizes and do that.
I can never remember what the megabyte limit is for WIGIO. It might be 25, so you can try.
Well, I'll still reduce it in case people want to download it, or just to be friendly. I mean, they don't need to be that size. I'll do that a little bit before I share it, but definitely we'll share it, and definitely I'm excited to answer more questions from you all or whoever else happens to watch this video online, and
thank you,
and responds later, and definitely look forward to it.
Excellent.
Yeah, and the links to the videos too, because sometimes those don't translate when you.
Definitely. Yep. I will definitely link to the videos. I'll link to a lot more videos. I'll link to the instrument websites I talked about. I'll link to, there'll be a lot of links up there.
That would
be
a
lot of different things that I'm involved in. And so.
Oh, good.
That would be fantastic.
You shouldn't come up with a lack of paths to go down if you choose to go down them. Otherwise, let me know.
Well, sometimes rabbit holes can turn out to be separate places. Have any of you looked more closely at Jennifer's SDO? And I just put it. And by the way, SDO's full curriculum suite is in Wavelength now. I just finished putting it in. But it seems like there was an activity in there that did work with spectra, and so I was thinking this information might be really great. It seems like you make either you order or you make a spectrograph. And I know Krista Wolf, mark me if I'm wrong, Wendy, wasn't Chris talking about spectrographs in his NSTA presentation? I know he's doing something with Maven. I know they're going to do the atmosphere stripping model, but I thought he was going to do something about spectrographs as well.
The only thing I saw in the brochure was something about earthquakes and seismometers, so I don't know.
Seismometers, spectrographs, they both start with us. But somebody there I know is working with spectrographs. I'll find out who it was.
I know there are very simple EUV not UV, but visible spectrographs that you can make that just have a little grade. It was developed at last by Aaron Wood when I was there. That you just take the little transmission grating and just put it in a box and cut it out, and you can see the spectra.
That Aaron's lesson is in Jennifer's curriculum suite. Now that, because I was like, I spent so much time with it, I looked at all 16 modules. You would think I know them like the back of my hand, but I remember saying that, thinking, isn't this what Aaron did?
And there's different versions of it too.
Yeah.
Lots of different versions, but that's one I'm familiar with. I know she's done a lot and inserted a lot of stuff into curriculum and things.
So this will be very handy information for people who want to really talk more about, or have students that ask more questions about that as well. So. Well, thank you again. I know we just have a couple minutes left, but Ricky, I know, wants to ask a question for the community and talk a little bit about something very quickly about that we've been kind of brewing a little bit, and Ricky's been spearheading for us. So, Ricky, do you want to take a couple minutes to talk about that?
Yes, thank you. So we're trying to put together a little 5-minute video, promotional video for the community of practice. We're looking to add new members to our group, and we're going to make a video. It will be all recorded on Zoom, and we'd like a couple of teachers and maybe one presenter to do a little testimonial, or we can do it as an interview style. So I'm looking for teachers who would be, or presenters who would be willing to do about a 30-minute interview with me, just to put together a couple of minutes of video. And if you're willing, you can pick the time and the date, and I will send you a Zoom information, and we can do it on Zoom anytime that you feel you have extra half an hour to spare. And it has to be done this month, so we have a week and a half. So I'll put on video the dates that we have, and you can choose one of those dates in any time that's convenient for you. And I will send you the Zoom information and the questions.
Didn't you already post one of those to the YouTube channel?
You did not, I don't think. I did.
Okay. Because I saw you interviewing, I can't tell you who her name is, but there was something, I got the email that you had put something on the YouTube channel.
Yes, I did an interview with Rachel Zimmerman-Brockman, but that was for our S&D EPO diversity case. It was a great interview, so watch it if you get a chance, but it was for a different project.
Okay.
And I will definitely highlight anything that Rachel talks about. Rachel, I adore. Like, I love NSTA every year because I finally get to sit in the same room with Rachel and we get to talk and giggle and have fun. But Rachel is just, she's a phenomenal person. When she was 11, she's Canadian. When she was 11, she created, and I'm going to say it wrong, Ricky, so help me understand, but it was basically what it became an emoji board, is what we've done for people who did not have, they couldn't write. And so it was a computerized thing when she was 11, friends. And then she figured out how to make it print out so that it would translate what people were trying to say that didn't have vocal skills. Am I explaining it right, Ricky? I can find I have the website booked, but good night, Don.
Yeah, she talked about it on the interview.
Excellent.
And we did a couple of links to it. I think it was called augmentative communication programs.
Yeah, something like that. It's definitely she has a link here. I'll put it in my computer is so slow. Phil, can you stop sharing so that we can?
Sure can.
See, I'm sorry, I can't. They don't. The one thing about Zoom is that it asks you to be kind to one another, not take things.
Stop, Pandora.
So she's been, anyways, but you should totally watch the interview with Rachel, because she's one of the feminists, or one of the scientists that you want your students to know about. She's incredible, just all around a great human being. Anyways, that's my plug for Rachel. I clearly cannot say enough good things about Rachel. But she has worked really, really hard with this diversity piece and has a lot to say about it. So this is from Ruby Sky PI, and there she is as an 11-year-old, and so she has a great passion for people with different abilities, and helping all of us connect together. So she's phenomenal. But definitely watch it. Yeah, so we're looking. I hope that you will all respond to that. It is a great project, and we're just looking for a few minutes of. We promise we won't sell your email or anything like that. But any testimonial that you can offer to Ricky, he's been great at getting this all set up and getting to work. We are out of time. I was going to share the data from the survey, but I know, Diane, you came late, and Wendy, you were gone last time, but we just talked briefly about how much we miss seeing so many of our faces, and that there seems, we have a steady flow of everybody. We just don't all show up at the same months. And like I said, we know they're watching the videos. We can tell from the hits, and we can tell from the IP addresses that people are joining us post. But so we appreciate your input on that survey. Basically, what we got out of it was, of course, we would all like to, and I'm glad it's just us. We thought we might need to say something about the stipend and explain to newcomers what the stipend was about before, so that people didn't think that some people were getting paid to come to the meetings and some people weren't. But you all understand how that worked this last time. But the biggest piece that came in was that it just people's schedules, like Laura said last time, that it's having to pick and choose things to do. But one thing that Laura brought up last time, something to think about over this next month, is that Laura brought up the idea of doing a collaborative project together. And or was that you, Lynn? I know you guys kind of all said either, to be able to pick something and kind of work together and present it to your different classes or different audiences to maybe feel some interest in coming and sharing and having something different and new to kind of bring some juice into things, because, when people can't come, they're missing out on the good conversation, the good sharing. So, good. I'm glad that you're finding the videos helpful too, Diane. So anyhow, our next meeting is April 23rd, and Ricky will be pounding on all of your email box doors. So make sure to answer to him or answer his questions. And we know Ricky will make it fun and painless for sure. He won't ask you any dark secrets. Anyhow, our next meeting, did I tell, is it the 21st or 23rd? I probably told you, it's the 21st. I'm sorry, April 23rd is somebody's birthday. So April 21st is our next meeting, third Tuesday of the month. And please reach out if you hear anybody or can post on the Widgeo the fun time that was had by all and the great information they missed. Then maybe we can get people to I know it's hard too. Everybody's spring breaks are about now, and I know that's really hard. So my daughter's is over our next weekend. Ours is a late one this year. So all right, we'll see you next month. Thanks for joining us. Thank you, Phil, so much for joining us. And I know that many people will be logging in to listen to you and all the great information that you had. Celery is letting me know that it is indeed past 7:30. He's been patient long enough.
So thank you.
Thank you. You all have a good week. Good night.
I just looked and the KP has gone back up. It's back up at 8.
I saw that as well.
Good night, everybody.
Night. See you guys. Thank you.